Hello. Let's look at variance matters. So there's a number of ways you could bring this lens to bear. Obviously, there's standard deviations on the inter-arrival times. It's not clear that you could do much with that because that's going to depend on things like traffic and sort of attention to departure times on the part of patients. There is some variance in the registration process. It's only 2 minutes. And then there may be some way of taking care of some of this prior to the day of surgery, but I'll leave that for you to discuss. And then there's standard deviations on things like the sedation and the surgery. So there are a number of proposals that you could look into. Standardization of equipment, robotic surgeries, which bring less variability, possibly. And if you can motivate reductions in any of the standard deviations, then that certainly would be an option. Same with the cleaning, right? So look into those as a possibility. What I want to consider, though, is the BMI thesis of Paul Kanuja and co-authors in that journal article on which this case kind of relies. So I want to just walk you through the mean and standard deviation calculation for the base case. This information here is from a table that is present in that article. So here are the different BMI categories. There are the means. Paul supplied the standard deviations. And then this percentage comes from the case. Yeah, these are just numbers that were computed from the actual frequencies of the different BMI groups in the article. The variance is just simply the square of the standard deviation. And then I'm also squaring these weights here. So these are the weights of each of the BMI categories. That's the square of the weights. The reason I need that is, the weighted mean just uses the weight times the appropriate mean of the category. And so the mean of a weighted sum is the weighted sum of the means. But in the variance case, we've got the following. Let's find my pen here. So if I want the variance of a weighted sum, probably need to plug it in. So just briefly, the math here is the following. I'm just going to do it for 3 categories. So it would be A1 squared times the variance of x1 plus A2 squared times the variance of x2 plus A3 squared times the variance of x3. So I need these squares. These are the A1. This is A1 squared, A2 squared, A3 squared, and I need those variances. So that's how I'm getting the variance, the weighted variance, the variance of the weighted sum. And then, of course, you just take the square root of that to get the standard deviation. All right, so a relatively straightforward calculation using hopefully something you've seen in statistical analysis or similar course. What I'm wanting to propose is that we sort of unpool these patients. We separate them into 2 groups, and the idea here is that, and this is just one possible proposal, that we assign lighter or lower BMI patients to track A and higher BMI patients to track B, with a hope that we continue to get what we're previously getting in terms of the surgery count, let's say 5 surgeries per day out of track B. But maybe, and this is the big if, can we get a 6th surgery out of track A if we assign lighter patients there, because they're going to have lighter, shorter surgery times. So this is what I'm analyzing in the 2 BMI groups. This is the original data here. Here are your BMI groups. And what I'm doing is, I'm taking 50% of the patients, going from the top. So that is going to be all the underweight folks, all the normal weight folks, and then, in fact, I've got even 5% down here. So 30%, all the overweight folks, and even some obese. That's 50%. Sort of an indictment of our population, right? The fact that the median is obese. But the idea is that I'm going to assign those to track A, and then the remainder, which would be the remainder of the obese, and then of course all the morbidly obese, and assign them to track B. Now, if I do that same calculation that I've just demonstrated, what I get is a mean of 97.62. The mean with all patients pooled was 100.71, a standard deviation of 8.09. So if I split it up, it is lower for this track A group, the lower BMI folks, 97.62. Not much, a few minutes, but maybe 2 minutes could do it. That's the question. And then a standard deviation of 678, 679. And then correspondingly, the track B folks are going to have a higher mean and a higher standard deviation. It wasn't guaranteed that the standard deviation would be higher, but it turns out that way. So I want to use these and test this idea as a way of unpooling and sort of managing the variance. I'm trying to reduce the variance in track A by going after lower BMI folks. And the fact that the mean is lower is also helpful. And then hopefully I can get by with this higher variance in track B. Another idea I explored is to split it up by weekdays. So assign 20% of the patients from the top to, let's say, Mondays. And then the next 20% and the next 20% to Tuesdays, and so on. So ultimately on Fridays, you're doing the heaviest 20%, which would be some obese and some morbidly obese. Okay, so I'll leave it to you to discuss, this possibility. One way to test its value would be to use these values to see if you did have a Monday type setup and all the average surgery times at 97.55 with a standard deviation of 743, whether that allows you that day alone gets you 6 patients. So let's go into a model. I've got the base case set up here, and I want to explore in isolation now that split where lower BMI folks are in track A. So all I need to do to implement that is to go in here and just change the service time. So instead of it being 101, 809, in the spreadsheet, it's 97.62 and 6.789. And then for the B surgeries, I'm going to just change that from 101 and 8. Should actually be 100. It's now going to be 103.8, and then the higher variance as well. Okay, so that is my pitch, my proposal, just to see if that's correct. I'm hoping to get 5 surgeries in track B, hoping to see a 6th surgery in track A. I'll run this. Okay, let's set our limit at 570. Here's in red, and we're going to hit go. Okay, so it turns out that I only got 4 surgeries in track B. I was hoping to see 5, and I only got 5 in track A. I was hoping to see 6. The bottleneck is the anesthesia. And then the surgeons are also pretty heavily utilized. And the operating rooms are running at 76%. Okay, so I can rerun this with a different seed just to see if another pass maybe gets me that 6th, but it already is a concern that I only had 4 in track B. So this doesn't look to be a thrilling option. Just go into the projects here. Click on simulation main, change the seed. Just to something else. Let's make it 28 and run again. Got 5 here, got 5 here. And you can observe the flow times. So no evidence as yet of a 6th surgery completing. Where is the 6th patient? Waiting for an anesthesiologist here, and same here, right? This left number is the number of patients that are waiting to enter the block, and then the one on the right is the number of patients that have left the block. So it's just not even true that they've got anesthesia. Okay, so that's a possible variance matters type innovation that comes from that lens. And in the final clip, we're going to put together sort of a composite mix of some of these proposals. So I'm suggesting that you do analyze the proposals in isolation so you can see what the performance delta looks like on the flow times, on the number of surgeries, and then sort of put it together to assess what the combined impact of your proposal is.